Thank you for inviting me. So my colleague Lotfi Zadeh still receives an award per day from this and that, and he explained to me how that all works. He told me a joke, this Russian general had received a lot of awards, and then somebody said, "Wow, you must be a real hero, you know." I said, no, the first award was a mistake. And they gave me the second one because they were impressed by the first and the rest followed. So those things can usually be explained very simply. So I'll talk about compositional control synthesis and verification for networks. Perhaps a little more verification than synthesis, but there's a synthesis component too. So the general situation that we're trying to handle is having large systems, typically networks of dynamical systems, and how to, you can't apply standard control analysis or design techniques after a certain number of states. So how do we scale up? That's the main problem that we'll be looking at. And what motivates me for these types of problems is some earlier work on multi-agent systems, and more recently I've got involved in a number of synthetic biology projects where our main niche is actually dealing with multicellular systems, not just programming a genetic circuit in one cell, but having multiple circuits coordinate something with each other. You've been looking at problems of synchronization, pattern formation, etc. And so this is one of the projects. I'm not going to talk about this, but this is an example where a number of bacteria are pushing forward a robot just to provide the propulsion. And we are looking at problems of synchronization of these helices so that you get the maximum out of this arrangement. So things of that sort where there are many, many things. And another interesting project that I've been involved in recently is traffic management, where the question is how to design the traffic lights and ramp meters in a reactive way that respond to the current traffic situation rather than time of day arrangements that are typically done. And also to coordinate arterials that lead to freeways and the freeway on-ramp meters so that you don't have two separate control authorities, so you coordinate those two. Right now they are done in completely separate ways, and in fact they are handled by different jurisdictions. So the general approach to handle this large-scale issue is I'll be promoting a compositional bottom-up approach. Okay, so we'll start from properties of pieces, appropriate abstractions of them, and go to the next level type of thing, which is obviously not a surprise for this audience. But I'll talk about the specifics of this approach that I have been pursuing. And in doing so, we also exploit inherent system structure whenever we see one. And so that's a very important part of this talk, actually, recognizing important structural properties of particular networks like the ones I talk about here, and I'll show you some in the talk, and use those to simplify the synthesis analysis techniques. And so in identifying those system structures, we always rely on applications. They're always inspiring, and if you find an interesting structural property in one application like a traffic network, then it's good to express that in system theoretic language, and so some other applications can benefit from similar results. So the outline, basically two parts of the talk. The first talk is using subsystem dissipativity properties to certify network stability and performance. So this we will see is a highly scalable approach when the network has the right structure. And we will also see that this can be pursued with numerical large-scale optimization methods. So in the second part, I'll switch gears a little bit, and I'll talk about formal methods as a control and verification approach. And so I'm not going to claim anything new from the formal methods but in trying to apply those tools which are developed for finite state models to our continuous state models, there is an important step, which is the abstraction of a continuous model with a finite state model. And how do we do that is the main question. And we'll use some important structural properties to numerically simplify this problem a lot. Really a lot, significantly. And then I will tell you how we can scale up even further using compositional synthesis ideas that sort of mirror the things that we'll do in part one. Okay? So let's start with part one. So this will start with some of the things I've done earlier, going back 10 years or so, and bridge it with some of the more recent things that we've done, mostly making things more numerical. Okay, so starting with the very basics, what is dissipativity, at least for the benefit of new graduate students? So you have a nonlinear system model, you use an input, and you define an appropriate output as a function of the states. Okay, so you use input y is state. So dissipativity is a notion that goes back to the 70s, goes back to Jan Willems. So if you can find a function that is non-negative of the states, scalar valued, whose derivative along the system trajectory is less than so-called supply rate, a function of the input, scalar valued function of the input and output. Okay, so that's the notion of dissipativity. What is more important in dissipativity is the supply rate rather than the storage function, right? Supply rate, the storage function only helps you establish this property. What the supply rate does is every different choice defines a different type of correlation that the system satisfies between its inputs and outputs. Okay, so typical choices are quadratic. Okay, and we'll be focusing on those in this talk. So a quadratic function of uy, and so x is a matrix in appropriate dimensions. Okay, for the simplest case, you can think of single input, single output, where x is 2 by 2. But this could be a lot bigger. Okay, so there's no restriction whatsoever. Okay, so simple cases, very common cases of supply rates is if x has this form, then this quadratic form generates the product, right? So u transpose y, that's the special case of dissipativity known as passivity. If you integrate this inequality in time, this is basically the derivative of the storage function in time, right, as the system evolves. And so if you integrate both sides, what this is telling you is that the inner product of the input and output is greater than or equal to 0, or it has a lower bound that depends on the initial condition. Okay, so that's the kind of correlation you're getting in this case. So the inputs and outputs are on average having the same signs, right? Doesn't have to be pointwise, but when you integrate over time, the sign will be kind of aligned. Okay, L2 gain doesn't care about signs. X has this form. It basically gives you a supply rate of this form, and when you do that integration again, it tells you that the square norm of y is less than gamma squared times the squared norm of u. That basically gives you a bound on the amplification of the signal. Okay, so the gain is more about how much the signal can grow from the input to the output, and passivity is more about what the signs are and doesn't care much about gains. Okay, so that's a crash course. So now what I'm going to show you is very basic. So let's say we have a number of subsystems. They are dynamical systems in themselves. And you stack up their inputs into a big vector u, and their outputs into a vector y. And then you close the loop with this matrix G. Okay, so G basically tells you which outputs go into which inputs. It can be any linear combination of outputs that feed back into a linear inputs. Okay, to simplify the problem, you can even think, I'm not going to do that, you could think that G has 0 diagonals, because then your output you can include it in this model itself, right? So G is basically the interaction part of it, and these are the individual subsystem models. Okay. Now, in typical applications, the systems may not have well-defined inputs and outputs. So you may have a huge model. You may be breaking it up into a form like this. So you may be defining the inputs and outputs artificially in a way that this describes an interconnection of pieces. Okay. So if we assume that each subsystem satisfies the dissipativity property of this form with an appropriate supply rate defined by the quadratic form xi, the question we're asking is, could we add up these storage functions for individual systems to generate a Lyapunov function for the whole system, right? As a first problem to pose. So when would this serve as a Lyapunov function? Okay, it is a very simple thing. You just add these things up. So in the end, the derivative of the Lyapunov function is bounded by a sum of these things. And then you remember that u's are actually dependent on y's. You substitute u equal to gy. In the end, you will get a quadratic expression like this. You want that to be less than or equal to 0, right? Very simple, very basic, and things like this have been done. So that will be sort of a starting point for some of the things that I'll show you next, right? So there's nothing in itself that is very, exciting about this. It's just a linear matrix inequality that tells you whether you can guarantee stability or not for the whole, right? So the question is, can I find x's like this, right? So what I'll do first is I will show you some specific interconnection structures that define G that go with certain types of supply rates, and I'll show you applications where those arise. Okay, so So first and foremost, an important class of coupling is when the interconnection matrix G is skew symmetric, so it satisfies this. Okay? When that happens, I'm not going to do this, but you could do it on your own in 1 second. If G has the skew symmetric form, you can show that if the X's have this structure, the passivity structure, then this follows immediately, right? Just from the skew symmetry of G without any further restrictions on G, and that particular type of X, you'll get that for free, okay? So again, very simple, but it actually is very useful, and I'll show you some applications where that is useful. So one particular case where I found that very useful was in multi-agent systems, and I'm basically going to show you a caricature of what's in a paper with many more details, of course, so oversimplification in a sense. So here you're trying to coordinate the motion of several agents, right? So X represents a vector of their positions, and then X dot represents their velocities, okay? And U is the force input to each. So basically you have these individual decoupled dynamical models. And you know, for a lot of mechanical system models, you will have passivity from the force input to velocity, basically based on energy dissipation properties. Okay, so you can take passivity for granted for these blocks. And integrators are also known to be passive. They are probably the simplest dynamical examples of passive systems. And in the feedback, you have the so-called graph Laplacian matrix. Okay, and the Laplacian can be decomposed in this form where E represents the graph incidence matrix. Okay, so if you do that and if you swap the order of these two, you get a structure like this. So E transpose appears here, negative E appears here. All you've done with this swapping is instead of dealing with absolute positions, you're now dealing with relative positions, right? You've defined the number of relative distances between the agents, and that becomes the new output vector. And that's what matters, because you're not trying to control the center of mass or anything. You're just trying to coordinate the relative motion. And with that, you can stack up all these passive blocks and the integrators, which are themselves passive, into a form like this. And the coupling matrix G will have this form, where E is the incidence matrix. Doesn't even depend on what the graph is, what E is, right? So by its very structure, G will be skew symmetric, and that's it. Okay? So that means, you know, the passivity properties here are compatible with the interconnection structure. So stability sort of descends from the nature of the thing, right? So you don't have to do anything pretty much. But using this idea, we've developed a number of redesign tools, adaptive and robust designs, synchronized path following, etc. So for multi-agent systems, and they are summarized in a book that came out a few years ago. So the main idea in much of this work is really some fancy generalization of this. You know, we have these adaptive loops that estimate parameters, this and that, and in the end, the overall block diagram still preserves that skew symmetric structure.
So you mentioned the E transpose as being the graph Laplacian.
Right.
Usually we encounter conditions about connectedness,
right.
The graph implying something about spectrum.
Mm-hmm.
You don't need those things here in this context?
You do, depending on, I mean, this is an oversimplification, you do depending on what you're trying to show. You know, with this you only get stability, you may get two clusters, right, if it's not connected. So I'm kind of brushing those under the carpet. All right, so I'm not going to go into the details of this, but for example, we've extended the same ideas to attitude coordination of satellites, where things are now in SO3, and so these blocks now become different. You know, they describe dynamics. We use unit quaternions to describe them, and instead of the incidence matrix, we have to define something called the rotational incidence and so on, but really the same block diagram at the end of the day. Okay, so another situation where I found this skew symmetry natural was in congestion control. I know a lot of people here were working on this problem way back in more than 10 years ago when it was very popular. So in the congestion control, the users is like the internet, right? So the users adjust their sending rates, which is a vector x here, and they receive prices, which is typically the total price they are receiving on the way, packet loss or drop rate, and use that to adjust, right? So basically each one is an algorithm that sets x based on the feedback Q they are receiving, right? They're all looking at their own individual entry of Q, right? R is a routing matrix that consists of ones and zeros, and so when you multiply R and X, you get a vector of the rates on the links. So it basically routes the individual sending rates of the users to the links, okay? And now you have the routers set their prices, right? So these are all distributed algorithms in themselves, and they each set a price. Now the feedback to each user is the sum of the prices on their way, on the links they are using, okay? And that can be captured with the transpose of R. So if you transpose R, you multiply R transpose with the price vector, you receive the individual prices for each guy, right? So in the end, the feedback loop has this form. And so skew symmetry again comes for free no matter what the routing is, okay? So it's in the nature of the thing. So back then with my colleague John Mann, we said that, you know, if you design these algorithms to be passive dynamical systems, you know, at the time people were trying to prove stability properties, building fancy Lyapunov functions and so on. We said that it descends again from the structure of the system. All you have to do is to make sure that the protocols you're using for the routers and the users satisfy a stability, the passivity criterion. And we showed that a lot of the existing things actually do, and so on and so forth. So that's been a while, so I'm not going to go into the details of this. So another network structure which is not skew symmetric. Okay, in all the skew symmetric cases, passivity was enough. Now we need a little more. So we'll talk about the so-called cyclic coupling structure. This is work I did with Eduardo Sontag again quite a while ago. So our motivation initially was oscillators in biology, and also there is a version of this in electronics, the ring oscillators. So they are all based on a cyclic coupling structure. In metabolic networks, there are all these variants of these cyclic couplings, you know, branching and coming back, etc. So how do you analyze the stability of these things, right? How do you know that you have a limit cycle or not? Instead, you go to equilibrium point, right? So in this case, for this kind of cyclic coupling structure, you no longer have passivity solving all these problems. You need a strict form of passivity where you need this strictly negative term here, okay? And with that, passivity, you know, from the condition that I showed you several slides back, coupling the interconnection structure with the dissipativity properties, this tells you that stability comes if this condition holds, right? So the negativity here I represented as gamma inverse. The reason is that the output strict passivity property implies also an L2 gain, basically from a simple completion of squares argument. So if you have passivity with this supply rate, you also have an L2 gain of gamma. But you capture a lot more than just a gain, right? You capture two things, both the sign preservation property and the limit on the amplification property that's embedded in this gamma. Okay, so there's a lot more information going on in this X, right? So now this is 1 over cosine, right? So it's a number that's always bigger than 1. In the special case where the number of systems is n equal to 3, then this number, for example, becomes 8. So it's always useful to compare this to small gain conditions for feedback loops, because small gain conditions restrict the loop gain by 1. In this case, we can go a lot higher. Okay? The reason is we are not using the gain alone. We're also capturing some phase information or the sign information, and that's what's relaxing this. Okay? So, and later on, I did an extension, mostly motivated by a synthetic gene circuit that I've been working on for the past n years. I mean, the theory was done in 2 weeks. The building of the thing proved to be. Of course, I was naive about synthetic biology. I still am. That's why I didn't pull the plug yet. But still, we're trying to implement a version of this. Anyhow, for the stability properties of this, you get 2 loops interconnected with each other. So I extend this condition to a class of incidence graphs that I call cactus graphs. What that means is that two cycles of the graph can connect only at one point, at one node. Okay, and these are examples. When you draw examples of this, they look like cactuses, and that's why it's called a cactus graph, I guess. All right, so now coming to something a little more recent. So this is a recent formulation that I've been pursuing with my colleague Andy Packard and a postdoc who has left, Lessard, and Chris Meissen is a student working with us. So now we're posing a more general problem. So suppose we suspect each subsystem has some useful dissipativity properties, and we have this interconnection matrix, right? And in an earlier slide, I showed you how you can use these dissipativity supply rates to form a stability condition. We pose something a little more general. I won't even specify what it is. It includes stability as a special case, but we can also ask performance questions. So we can add disturbances into the system, define performance outputs, and we can ask for some, say, an L2 gain from a disturbance to an output, etc. Right? So, but at the end of the day, what you're trying to prove for the whole network is some linear combination of these supply rates. Okay? So a class of problems that can be brought to an inequality of this form. All right? Now, what we're saying is, in the earlier examples I showed you, G had a very specific structure, and we knew that that structure favored some certain dissipativity properties, and we knew what to look for in the subsystems, right? Now, in this scenario, you know nothing. I mean, you have a bunch of dynamical systems, and you're just trying to certify performance of the interconnection. You don't know much about the subsystems. You know their dynamical models. Okay, so basically you want to search for useful dissipativity properties over the system. So basically for each subsystem, you're looking for a useful storage function as well as a supply rate that satisfies this. Of course, there isn't only one pair, right? There are multiples of them. So which ones are useful in the sense that they allow me to certify this stability or performance condition for the network, right? So that's the problem. Okay? So I know the interconnection. I don't know what these are. And I don't even know if the subsystems have any of those or not. Okay? So you can turn these problems into semi-definite programs. If they are linear systems, it's a simple LMI. Okay? If they are nonlinear systems, you can use, if they are polynomial systems, you can use sum of squares techniques to turn it again into a semi-definite program. Okay? Those usually fail for large systems, but that's the whole idea in this formulation, because this is, you know, you're breaking up a big system into smaller subsystems like that you can handle individually. Okay? So these problems, let's assume, are small enough that an STP solver can handle. All right? But when you put them together, it can't. A typical scenario in analyzing networks. Okay? And the reason is that, you know, you have a bunch of them. They look like they're independent problems, but they couple through this constraint. Okay? So doing it blindly will not take you anywhere. Okay? So we started seeking an appropriate decomposition of the problem, and the problem already suggests an appropriate decomposition because these components are almost decoupled, right? Except that they couple through this one performance constraint. Okay? So in the end, the decomposition we came up with is this one. So what we do is, instead of these x's, we define a master program that works with a proxy, say z. Okay? So this basically looks for supply rates that would have been useful for the network, whether the subsystem has those or not, right? And then the subsystems, for each you have a parallel program, an SDP basically, that's looking over the supply rates and the storage functions to verify such properties. Okay? So that's the decoupling idea, and of course at the end everything has to come together, so we embed this into this constraint z equal to x. Okay? So this is basically a very standard idea, and some people in optimization call it divide and conquer instead of conquer, because you have to conquer z being x. So you divided it by defining this z, an auxiliary variable, and in the end you just want to make sure they match, right? Okay, so there are several distributed optimization methods that are applicable to this type of decomposition. One we found to be particularly useful was ADMM, and I'll tell you in a couple of slides how that works very simply. But at the end of the day, I think it's more important to understand the main concept. So what's happening is we have a master program. It's proposing a set of supply rates that would have satisfied this performance objective, right? And then the subsystems are looking to see if they actually satisfy this. If they don't, they say, what about X? I have X. Will that work for you? Okay, so they kind of have a negotiation between them. Okay, so the rest of the slides are basically an optimization, trying to put this in a standard optimization formulation and do it with ADMM. So, but the main idea is in this slide, so I can go maybe a little faster. So this is a standard optimization formulation to which ADMM is applicable. You know, a problem of this form. Okay. Now, in our case, we actually have a feasibility problem. We are not trying to optimize anything in particular. So to go from optimization to feasibility, a standard way, just for an appropriate formalism, is to define indicator functions. So since in my case there is no objective, the question is whether I satisfy the global constraint or not, right? So I define an indicator function that is 0 if the global constraint is satisfied, infinity otherwise, okay? And don't let the infinity scare you. We're not going to see the infinity ever, because that all that means is we'll do our search within the feasible space, okay? This is just to match the two formalisms. All right, and so that will be part of our formulation. And then this part is the part about subsystems. Do you have the dissipativity property defined by X or not, okay? And the key in this algorithm is that this decouples to each subsystem. So this d of x is the sum of individual subproblems for each subsystem. So the decoupling here is the key, because that way you can handle as many subsystems as you want, because you're running parallel programs for each. Okay? And finally, we have the constraint, and the constraint basically translates to z equal to x, right? So pretty much a more detailed version of the previous slide. So what does ADMM do? For a standard problem of this form, it goes in 3 steps. So first you search over x, try to minimize the dx component. In addition, you have a regularization term that tries to keep you close to the constraint, right? So ax plus bz need to be close to c. If they are not, then that becomes part of the formulation, right? In addition, there is this u term. People don't usually use the letter u, but I do, because this almost looks a little like integral control, right? Where if you stray from the set point, you want to integrate that and make sure that it's eventually satisfied. So this part of the algorithm resembles, in an eerie way, integral control, and then it also feeds back into this, all right? So when you adapt this formulation to feasibility problems like ours, d of x or g of c they are indicator functions, right? All that means is search within the feasible set. Try to minimize this within the feasible set. That's all it says, all right? And rho becomes irrelevant. It's just a scaling factor. So for our case, the regularization parameter is actually irrelevant, okay? So translated to our case, the subsystems are trying to find dissipativity properties, x, that are close to what's proposed by the master program, okay? The master program is collecting everything that the subsystems find and report back and trying to see if that works. If not, it's trying to propose something that was as close as possible to what was reported to them. And then with this additional integral step, you go back and the subsystems again try harder to come close. Okay, so that's the negotiation that. So remarkably, I'm not an optimization guy, but I've learned that the convergence conditions for ADMM are pretty much nothing. It converges. I mean, the assumptions are remarkably mild, and there is no parameter tuning or messing with step size schedules, etc. It just seems to be plug and play, and I think that's why more and more people are using ADMM in various applications.
Remark on how the linear constraint ax plus bz is equal to c showed up in this. Not just the x is equal to z, xi is equal to z.
No, I just show you the general formulation.
Yeah,
ours is special.
The previous slide also, you had that constraint on the left-hand side.
Right, so I said this is the general form to which ADMM is applied. For us, it just is z equal to x. There's no c for us.
Okay, so it's really the z equal to x constraint.
That's all for me.
In terms of the more general.
Yes, yes. So ours is a very special case. All right, so we want to try it on something challenging, so I want to stress test this a little bit. So we gave it a problem, it being the ADMM algorithm, that we knew the solution to. Always works in academics, right? But we also knew that the solution set, the feasible set, is very narrow. Okay, we constructed it as such, and we wanted to see if it will actually crash or it will find the narrow solution, right? The problem was this: a skew-symmetric interconnection. Why? Because I have the intuition about them. So we tried 100 randomly generated skew-symmetric interconnections of 50 subsystems. Each had this simple linear form. Okay. The way we constructed those is that we know they are passive. It's constructed as such. But we choose these diagonal entries so small that we also know their L2 gains suck, right? I mean, they have huge gains. Okay? So we know that anything that uses gain in the loop will not give you anything helpful, especially with this kind of large interconnection, right? The gain properties all particularly fail in large interconnections because then the norm of the matrix comes into play. That also introduces some gain, and that increases as the number of agents increase, right? the advantage of passivity was that, you didn't care if you had this skew-symmetric interconnection, how many agents you had, right? So that was the idea. Epsilons were small. They were also randomly generated. And it found what it knew was the solution. I mean, it doesn't give you exactly this. It probably gives you 0.001 or something like that. But gives you something that works. So it does detect that very...
But you won't be surprised at this thing, right?
No, I'm not sure. I mean, I knew the answer. No, but okay, so...
The passivity is going to be that. There cannot be anything else.
Yes, but that's the whole point. So you're kind of stress testing the algorithm with a problem which we know has a very narrow feasible set. Okay? But yeah, I mean, totally cheating. I mean, you're right. Okay, so something we've done very recently, I'm not going to go into the details of this. So we realized that in these problems we can do further reductions of the problem size by exploiting symmetries in the interconnection. For example, the cyclic interconnections that I showed you earlier and that secant condition that mysteriously popped up, that was really basically as a result of using the rotational symmetry in the interconnection. So we want to formalize this a little more. So we looked at networks with disturbances and performance variables defined. These are the performance variables in this case. And if the interconnection structure has some interesting symmetries, then you can use this to reduce the problem, the stability or performance certification problem. In this particular example, you have this left-right symmetry. That means you can lump these into one supernode, so to speak, and look for the same supply rate for these two subsystems. Okay, that leads to some savings in the computational complexity. So I'm not going to go into this. All right, so part 2. Any questions about part 1?
So
yes?
You need discrete rotational symmetry in the
Yes.
case?
Yeah. Not as it is because there's a negative sign that breaks it, but we can also use transformations, complex ones, that create symmetry while not changing the stability condition. In this case, that negative one is distributed over the links with a partition of unity as complex numbers.
So what kind of symmetry you can do this way?
Rotational is one. We look, in that case, it's not particularly exciting, but we can also look at platoons. Then there's this left-right symmetry if it's a bidirectional communication.
So if I look at the variables x1, x2, and the original problem, can I formulate the problem if I have the graph on a more general symmetry group, or just have to do the binary and simple things like that?
Yeah, if you know the symmetry group, you can formulate it in the first place like
So
that.
you know the graph, right?
Right. I mean, it's not easy to enlist all symmetries manually, but there are software that enumerate all the symmetries. So
And then if you have a more general symmetry group, and you go to the graph and you do the reduction, if the graph reduces according to that symmetry group, then can it, again, ADMM give you anything different?
yeah, you can reduce ADMM, make it even simpler. That's all. That's all there is.
ADMM has problems with actually rigorous proofs of convergence, right?
No, that's proofs. I mean, I don't understand the proofs, but they exist. So.
The value or the solution?
Huh?
The value or the solution?
For several things, but people say the convergence is so important. I mean, I'd be happy if I get from either one of you that you know some proof that it's rigorous and I can understand. Because the ones I have looked at, they have gaps.
Okay, I mean, you looked at them more than I did, clearly. So.
I know more, but because
Okay.
for general non-linear problems where you have this kind of problem that I just described, then I don't know if you have proof or not. People apply it a lot of times blindly. They say convergence and that's the case.
Yeah, I mean, we can talk about it after about your criticism of the proofs. All right, part 2. So we started recently looking at formal methods as a new approach to, new to me anyway, control synthesis and verification. If you asked me 3 years ago, I thought formal methods was an esoteric, software verification type of area, but now I'm getting to appreciate it more. They have remarkably efficient tools for certification of, temporal logic statements as well as synthesis tools, right? The problem is you need discrete models. You need finite state models, and after that point, to me at least, formal methods is off the shelf. You just apply one of the existing methods for either verification or synthesis, right? So in our case, we're interested in continuous systems, and the problem that brought me to this was traffic control that I've been increasingly interested in. Things like control of signals at intersections, ramp metering for freeways, and their coordination, which is an important problem, especially near where I live, which is close to 80. I guess this is out of battery right now. So now for these types of flow networks, there are well-established macroscopic continuous flow models, and they've been validated to some extent, and we would like to be able to use those. But again, we need finite state models, right? So how do we bridge that gap, okay? So the usual step to go from a continuous model to a finite state model is the so-called abstraction, represent a continuous state, divided into appropriate bins, and model the transitions between them, okay? But that's extremely expensive computationally if doable at all. So that's a problem that we've been studying, mostly with this motivation from traffic networks, and we've realized that some interesting structural properties that exist in traffic networks help this abstraction step tremendously, okay? So I'll show you in one or two slides. Basically, at the end of today, the property of the network that we use is a form of monotonicity that we call mixed monotonicity. So let me first... Okay, so PowerPoint doesn't like monotonicity. That's interesting. I don't know what happened.
PowerPoint always converges.
That's right. There's a flaw in that proof too. You see it now?
And the application.
Okay. So let me very briefly reintroduce to those of you who are already familiar with it. I apologize for the repetition, but for others, what is monotonicity? So that's, again, an old concept that goes back to more Hirsch in the math department at Berkeley, who introduced these concepts, and later others worked on it. Most notably, recently, Angeli and Sontag did interesting work extending them to systems with inputs and outputs, etc. So if you have a discrete system, I'll just stick to discrete models right now. If you have a discrete system of this form, x plus means x at the next step, where x lives in appropriate state space. Monotone means that if you take two states where one is bigger than the other with respect to some partial order, then under this image of this map, that order is preserved. So monotone systems are naturally, as the name indicates, order preserving systems. And in this talk, I don't need any fancy partial order. I'm going to stick with the standard order, although everything I say is pretty much extendable to other partial orders. Now, monotonicity has been studied a lot, and it is known to have very important, useful convergence properties for dynamical systems and so on and so forth. Zillions of papers on this, but it is also quite restrictive in practice. Okay, it works for a certain class of systems, but it's not as broadly applicable as one would like it to be. It's easy to see why. From a necessary and sufficient condition that is well known for the case where the partial order is the standard order. In that case, you just look at the Jacobian of the map F, okay, and that matrix has to be non-negative entry-wise, okay? Okay, so that should give you an indication of why it's a little restrictive, right? So what we define is a relaxation or a generalization of monotonicity that we call mixed monotonicity. And I will go through the definition briefly. So we take this map F and we define another function, derive another function little f from that now has two arguments, okay, instead of just one. Okay, instead of x, we have x and y, let's say. Okay, when those two arguments are the same, it should collapse to the original map F, big F. And the new map we generated, little f, should be increasing with respect to the first argument and decreasing with respect to the second. Okay, so it doesn't all have to be increasing. You basically should be able to segregate increasing and decreasing components. Okay, that's all there is to it. So that's the purpose that the little map F serves. Okay, here's a sufficient condition that parallels the necessary and sufficient condition for monotonicity. If your map is such that the Jacobian has sign stability, meaning that the signs do not change as the states change, right? Pick a particular entry, it's always non-negative or always non-positive or always zero, things like that, right? So no sign changes along the way. If your Jacobian has that property, you can immediately argue that you have mixed monotonicity. The proof is constructed is basically this. You take the original map, look at the entries. If you find an entry with respect to which you are decreasing, call it y. Okay? And you're done. You've constructed your little f. Okay? Turns out in this case it's only sufficient. There are more creative ways of defining the little f even when this condition is not satisfied. But they are pretty much case by case, and I'm not going to. So for our talk here, this sufficient condition is all we need. Okay, so what does monotonicity or mixed monotonicity have to do with abstraction? Very simple. So if I divide my state space into bins, boxes, or whatever we want, and you want to know where this box will translate after one iteration in the dynamical system, right? Now, because the picture above shows that because the system is monotone in that case, if you take the two edges of your box, smallest and largest, right? And if you map those 2 points under your dynamical model F, those two will sandwich all possible points that anything in that big x1 to x2 box can land. Okay? It's an over approximation. It's clearly not exact, but it's tight in the sense that you actually meet the corners, right? The corners are part of the image. So there is no smaller box that would work. Okay? So if you're doing an abstraction based on boxes, that's pretty much the best you can do for a monotone system. Okay? Mixed monotone relaxes this to a bigger class of systems that we call mixed monotone. Now you have to evaluate the lower and upper points under the little f that we defined. And that will box, that image will box all other solutions, sandwich everything else. Okay? And again, you can argue that this is tight. That also takes a couple of more lines that are not shown here. That there is no smaller box that includes the whole image of the initial box. Okay? So that way, you know where, for starting in a bin, which other bins you can land in. Okay? At least you have an over approximation of it. Okay? Now, these abstractions always introduce spurious transitions, and in a sense, the synthesis and verification tools account for them, meaning that, you know, they guard you against something that won't happen, but that's fine if it's not going to happen, right? So there may be a little bit of conservatism in the construction or synthesis, but I mean it's a rigorous method. So if you get an algorithm that works for this transition, despite the spurious transitions, it works on the original system. So we showed that this allows a scalable abstraction algorithm. This was presented at the last HSCC, and the significant gains of this is that you need only 2 function evaluations. Okay, the closest existing result to this is applicable to piecewise affine models, and you do polyhedral operations to do this kind of mapping. Okay, and those grow exponentially. Okay, ours doesn't even grow. It's just 2 function evaluations. In addition, ours is also applicable to nonlinear models. We are not limited to piecewise affine or anything like that.
Piecewise affine in the style in which Berkeley and people do in Berkeley and people.
Yeah, and Colin Belt has done a lot of work with abstractions. So
there was exponential in the piecewise because, I mean, it depends on what you're trying to verify, because you know whether it's up or dead, right? You can actually solve many problems by just convex programming.
Right, but the vertices, I mean, the number of vertices grow, and you
can do very fast. It's going to be some sort of a simple convex programming program or piecewise affine approximations that can do millions of variables, millions of constraints. So how? Well,
for systems that are second order and so on, piecewise affine, you know, the abstractions that exist with polyhedral operations, they work fine. But for higher, I mean,
much higher than that.
Huh?
People have done much higher than that. In Grenoble, for instance, if you look at the results of Grenoble, they can do much bigger. You know what I'm talking about? But
I don't know.
But they matter.
Oh, it matters. Yes, of course I know. No, they can't go too far with the state dimensions. I mean, Colin acknowledges that he's done the piecewise affine.
Depends on what you're trying to do.
Right, but for what we're trying to do, it's pretty limiting, and this works pretty well.
I'm not doubting that it works.
Oh, okay.
When you said it grows exponentially, that's what I asked.